So I've been wanting to do a really cool experiment for a while now, but I just recently got the equipment to be able to do it. So basically what I want to do is take one element, in this case aluminum, and using radiation transmute it into another element, in this case phosphorus. And I don't know, I just think nuclear interactions, especially like turning one element into another, is just endlessly fascinating. So anyway, how you're gonna have to do this is essentially you bombard aluminum-27, which is the normal, most common isotope of aluminum, with alpha particles, or basically a helium nucleus, and that will transmute some of the aluminum-27 into phosphorus-30 and emit a neutron. And the phosphorus-30 is actually not a very common isotope of phosphorus. None of it exists in nature. It's all of it that exists is synthesized, basically, and it has a half-life of like 2.5 minutes or something. So the phosphorus-30, because it's unstable, will decay relatively quickly into silicon-30 and emit a positron. Which is beta positive, basically. So the positron, which is an anti-electron, will very quickly meet an electron just out in the environment and annihilate it with it, which will produce 2 gamma rays, each at 511 keV, which is the resting mass of an electron. So how the setup is going to work is we're basically going to put aluminum in close contact with an alpha source, and then take a gamma spectrum of that over a long period of time and look for an increase in this peak at 511 keV, which would be indicative of the annihilation, which would result from phosphorus-30, which results from the aluminum being transmuted by the alpha particles. So I'm going to use my spectroscopy setup that I have over here, which I've been working on a lot over the past few weeks. So on the bottom, we have a lead castle, which has about 30 to 40 pounds of lead, which is basically about half as much as I really should have, but I just don't have that much right now. Then I have my detector, which I made a couple weeks ago. It's a 1.5 inch diameter by 3 inch sodium iodide thallium doped crystal coupled to a PMT. Then my multi-channel analyzer is a Canberra Series 35, which interestingly belonged to the University of California in a past life. This was donated to me by a very generous benefactor, along with the crystal for the scintillator, which is pretty much the only way I was able to afford this. So high voltage comes from this high voltage power supply, which is occupying this NIM slot in the back of the unit. High voltage comes out of the SHV connector, goes into the splitter box that I made, which provides power to the PMT. It requires about 800 volts to operate. Then the other end of the splitter, the signal, goes into the amplifier input on the back of the unit here. I will use this to acquire all the data, and then there's an RS-232 connector on the back, and I will use this circuit here to get the data onto my computer for further analysis. So yeah. So to do this experiment, we do need a relatively high, or at least reasonable activity, alpha source. So I have over here 4 of these americium buttons that I took from smoke detectors, and each of those is roughly 0.8 to like 0.96 microcuries, so I've got between 3 and 4 microcuries there, and it is relatively high activity. So if I cover a piece of paper, and here's my Geiger counter, it has about a 1.5 inch diameter mica windowed Geiger tube on the back, so it's sensitive to alpha. Background is between like 50 and 75 counts or so right now. With paper over it, we should only get the gamma. There's a 56 keV photo peak from americium 241, which is what most of those are. So we're getting around 3,000 counts per minute just from the gamma. So I take this piece of paper off, now we can measure the actual alpha coming off of it, and you can see already it just totally dwarfs what we were getting with gamma. It's approaching 350,000 counts per minute, but actually we should be getting much more than this. With this Geiger counter, just one of those Amerisym buttons reads as about 150,000 counts per minute, but there's just so much dead time, and the tube is becoming so saturated that we're losing, you know, almost basically a source or two worth of counts coming off of those just from pure dead time, which is kind of crazy, but so our specimen is just our alpha source, which we saw earlier, with the aluminum foil over it, and some of that aluminum, at least a few atoms, will hopefully transmute into phosphorus 30, and that should produce a detectable annihilation peak, hopefully. So I'm just gonna go ahead and load that into the castle. I have the preset set for 18,000 seconds, so hopefully, that's 5 hours by the way, and hopefully that will be long enough for something noticeable to be detected. So just to be clear, what we're expecting is a peak here, at least a little bit above background, hopefully a couple sigma, or well, at least 1 sigma, and it will probably take it quite some time to accumulate. So hopefully 5 hours will be enough, but I guess we will find out. So yeah. Okay, we have now been collecting data for 18,000 seconds of live time, or about 5 hours, a bit more 5 hours in total. What we can see in the spectrum is there's something of a continuum continuing down here. We adjusted the discriminator so that we wouldn't get the main photo peak from the Amerisym, because that would have just totally overpowered everything else, and we didn't really care about it. So on the far left, I've selected this one region of interest, because I thought it was kind of interesting. It's just a potassium-40 photo peak, which is very typical of background situations like this. We also see the peak that we were looking for at 511 kV right here. Our calibration is a bit off. It says 505 kV, but there's nothing really with a photo peak around there that we could expect to occur from naturally occurring radiation, so it's much more likely that it's the 511 kV annihilation peak that we were looking for. So if I zoom in to the highest scale, you can see this peak is pretty noisy, but it is you know, pretty readily noticeable on this spectrum. It's at least as noticeable, or it's probably actually larger than the potassium-40 peak, which we definitely know exists. So there is something here, and if we hit the area integrate button, basically what this does, this number represents all of the counts within this whole highlighted area, and then this number represents all the counts basically above a line drawn from the background here to the background there. So it's an approximation of what this would be if this sort of continuum that it's sitting on top of just didn't exist. So we can expect that we got approximately 300 to 310 counts from our actual, we'll call it antimatter reactor that we have in there. So what we're going to have to do is do a background subtraction so that we can be totally sure that this wasn't just something which is occurring normally in background, or otherwise from something else in this room, or from the alpha source, or what have you. So I will do that next. So we now want to subtract everything in that spectrum that wasn't that one photo peak, or basically anything that wasn't created from the transmutation of aluminum. So we're going to do a background subtraction, which in this case means running another 5-hour spectrum with the alpha source, but without the aluminum on top of it. And that way it will subtract everything from background and everything from the alpha source that was not being produced, basically, from the transmutation of the aluminum sitting on top of it. So we will just take this guy, pull the foil off of there. The foil still looks pretty much normal, unsurprisingly, so we'll pretty much just push that right back in there. And I am going to put this piece of paper on top of it, which should block the alpha, so hopefully that will block any weird alpha-related effects, and we will only get, or be subtracting things that are being created from background and from the americium source itself, which we do not want in our final results. I think we are good to go, so I will just set this on subtract now, and we should begin a background subtraction for another 18,000 seconds of lifetime. And if all goes according to plan, if we have created antimatter, basically this continuum will go away, this potassium 40 peak will go away, but this peak should still be there. Whether it is still there or it's statistically significant afterwards, we don't exactly know. Like, looking at this, it really looks like we've made something pretty statistically significant, but we can't quite light the victory cigars quite yet. We need to do a subtraction to make sure that there's not something we don't expect going on. So I will just start that now, and it's pretty late now. I will check back up on this in the morning when this has completed. Alright, so our 18,000 second background subtraction is now complete, and as you can see, the spectrum now looks quite different. If we switch to logarithmic mode, it's pretty much, the continuum has pretty much completely gone. I mean, it's still there, but it's really low. The potassium 40 peak is pretty much gone, and zoom back in, like there might be a bit left from it, but with the peak that we're looking for, it has gotten quite a bit smaller, which, yeah, we'll have to look at that. It is still sort of discernible in the spectrum, though, so just because it looks like it's there doesn't necessarily mean that it's significant, so we're going to have to load this onto the computer and do some more statistical analysis on it. Alright, so as I mentioned earlier, we are going to need to do some statistical analysis on that peak we got, just to ensure that it is actually real, and not just basically random fluctuations or whatever causing it. So what we're going to do, this is just an example spectrum to sort of demonstrate the point. Each of these lines represents a channel, and then the height of the line represents the number of counts, just like the normal spectra. So let's say we have this example spectrum, and we think that we have a peak in where the channels are blue here, or we expect to get a peak there, whatever. So in any case, we have an ROI there, and we want to know whether there are statistically significant counts in there above background. Basically, what we can sort of try and do is use the background around the peak, which are these purple channels here, to sort of try and interpolate what the background would have been across this area if this weren't here, and use that to derive a limit, like where like above this line everything is like statistically significant to within like a certain percentage of confidence. So yeah, basically how this works is you would find the mean of the background on the left and the mean of the background on the right, and use that to derive this line here, which is pretty straightforward, and you would find the area under this line and that would be the background you would expect or you would predict based on just the things that are going on around it. And from that, you can use a standard formula to derive how much above that line counts need to be considered significant within a certain percentage of confidence. Then we're going to use this formula to figure out how many of the counts that we have are actually statistically significant. So the ROI sum, or the sum of the region of interest, that's where we think the peak is going to be, is this total area, everything in blue, minus our predicted background, and that'll be the ROI sum. I should say net sum, but good enough. And we're going to use this formula to figure out sort of the offset it needs to be above the predicted background in order to be considered significant. So we're going to multiply the square root of 2 times the background, which is just sort of a standard formula for this sort of thing, by 1.645, which is basically the z-score for 95% confidence. So we subtract our predicted background, the value required to be 95% confidence. It's not just random fluctuations in background, and that will give us our real counts, or our counts that we're 95% sure are significant. So if we come on over to the computer, I've loaded our spectrum data into Excel. So this was the data that we originally had before the background subtraction. You can see this was the 511 peak we were looking for, and this was the 1450 potassium 40 peak. This was after background subtraction. The peak that we were looking for is here, so it's definitely gotten a lot smaller, which tells us that the americium source, or just background in general, had contributed to that peak in some way, which is a little bit interesting. But anyway, this peak is still sort of visible, but it's hard to be confident how significant it is, which is why we have to do all our calculations. So this graph here is basically just zoomed in from the other graph on our region of interest. So this is the mean for the background on the right. This is the mean for the background on the left. There are a lot of things that just got subtracted out, so even though a lot of this stuff is above the mean, a lot of it's just sitting at 0, which is why this line ends up being relatively low. This right here is where we would predict the background to go, and we're going to use that to calculate the area under here for the predicted background. And basically we're saying that the peak that we think we're getting is between like this point here and this point here, which is not too unreasonable. You can sort of see the shape of the peak there. So basically this is the mean of the background on the left. This is the mean of the background on the right. This is the total area under where we think the peak is. This is the total area under the other background, and the this was the right background, or the left background I mean, and this was the right background. You'll notice it's pretty big compared to our actual peak, but that's mostly because it just takes up more channels. So here we go. So this is what we predict the background to be under that area based on the area under this line here. And then this is the offset that we need above. So like this plus this subtracted from the total integral will give us the number of statistically significant counts. So when we subtract those two numbers from our integral, we get about 25 to 26 counts that we can be confident, or 95% confident, were actual counts above background. So we do have some statistically significant counts resulting from that peak, which means we can be 95% confident that at least some of the radiation that we were detecting was the result of phosphorus-30 decay. Now, if we were really good scientists, we would run this experiment a few more times, but because I'm lazy, I'm just going to call that good and say that we were transmuting some aluminum, which is pretty frickin' sweet when you think about it. We were making a new element from another element.
It was the miracle that eluded the alchemists.